So, what do a planet's orbit, a satellite dish, and the path of a comet all have in common? Well, the answer is kind of surprising. It all comes down to slicing a simple cone. Today, we're going to dive into these beautiful and super powerful shapes, conic sections. So, here's what we've got on tap. First, we'll look at where these shapes actually come from, visually. Then, we'll meet each member of the conic family one by one. After that, we'll get into the algebra, the language they all speak. And to wrap it all up, we'll see how this math isn't just for textbooks. It literally shapes the universe around us. All right, let's kick things off. Where do these shapes even come from? It all starts with one single 3D form. Okay, I want you to picture two ice cream cones. You know, the classic pointy ones. Now imagine one is flipped upside down and they're balanced perfectly, tip to tip. That shape, that's what we call a double cone. And believe it or not, this is the parent, the single source for every single shape we're talking about today. Now let's get into the fun part. Imagine taking a knife, a perfectly flat plane, and slicing through that double cone. The magic here is that the shape you get depends entirely on the angle of your cut. So if you slice it perfectly flat, perpendicular to the axis, boom, you get a circle. Easy enough, right? Now, if you tilt that plane just a little bit, that circle stretches out and becomes an ellipse. Tilt it even more so your slice is parallel to the side of the cone, and you've just made a parabola. And finally, what if you go really steep? So steep that your slice cuts through both the top and bottom cone? That's how you get a hyperbola. It's amazing, right? Four totally different shapes, all coming from this one object. Okay, so we've seen how they're made. Now let's get properly introduced to each of the four members of this iconic family. First up, the one we all know and love, the circle. The definition is just so simple and clean, right? It's just all the points that are the exact same distance from a single center point, and its equation is just as clean. X squared plus y squared equals r squared. Next up, we have the ellipse. You can really just think of it as a squashed or stretched out circle. Now, an ellipse has these two special points inside it called foci. And here's the cool part. If you pick any point on the edge of the ellipse and measure the distance to each focus and add those two distances together, that sum will be the sail no matter which point on the ellipse you choose. And check out the equation. It looks a lot like the circles, but you can see those squared terms are being divided by different numbers. That's the math telling you about the stretch. Then there's the parabola. This one's pretty unique. Every single point on this U-shaped curve has this really cool property. It's the exact same distance from a single point, the focus, as it is from a specific line called the directrix. This is not just a math trick. It's why satellite dishes work. They're shaped like parabolas to catch all the incoming signals and bounce them all to one single spot, the receiver, which is placed right at the focus. And last but not least, we have the hyperbola. It kind of looks like two parabolas facing away from each other. Just like the ellipse, it has two foci, but here's the twist. Instead of the sum of the distances being constant, it's the difference that stays the same. And when you look at its equation, there's a dead giveaway, that big minus sign between the x squared and y squared terms. You see that? You know you're dealing with a hyperbola. So, we've got the visual, the geometry down. Now, let's switch gears and tackle the algebra. The big question is, how can you just look at some random equation and know instantly which of these shapes it is? Well, this right here, this is the master key, the blueprint for every single conic section, every circle, every ellipse, every parabola, every hyperbola. They can all be written in this general form. And the secret to telling them apart, it's all hidden in the coefficients, specifically those numbers we're calling A and C, the ones right in front of the x squared and y squared terms. This gives us a really simple checklist, a little test we can run. So look at A and C. If they're exactly the same number, you've got yourself a circle. If they have the same sign, like they're both positive, but they're different numbers, that's an ellipse. Now, what if one of them is just gone, like there's an x squared but no y squared? That's a parabola. And finally, if A and C have opposite signs, one's positive, one's negative, it's got to be a hyperbola. Simple as that. Okay, theory is one thing, but let's see how this works in practice. Time to put these rules to the test with a few examples. All right, first one. 4x squared plus 9y squared equals 36. So let's use our test. A is 4 and C is 9. Okay, they're both positive, but they're not equal. Our rules tell us that's the signature of an ellipse. And just to be sure, we can get it into that standard form by dividing everything by 36. And look at that, it matches the ellipse formula perfectly. Next up, x squared minus 4y squared equals 16. Right away, that minus sign between the squared terms should be screaming at you. It's a huge giveaway. Our coefficients, a and c, are +1 and -4. They have opposite signs. That is the classic fingerprint of a hyperbola. And again, if we divide by 16 to get it into standard form, it just confirms what we already knew. And for our last one, take a look at x squared equals 8y. So, what's missing here? You see it? There's no y squared term at all. That means our coefficient c is basically 0. And that, right there, is the defining feature of a parabola, no doubt about it. And since it's the x that's squared, we know it's a parabola that opens either up or down. Before we move on, let's talk about a few common mistakes people make. The biggest one by far is mixing up ellipses and hyperbolas. Just burn this into your brain. Plus sign means ellipse, minus sign means hyperbola. Another thing, don't forget that a circle is really just a super special, perfectly symmetrical ellipse. And finally, please remember to divide everything to get that equals 1 on the right side. That's what puts it in standard form, and it makes life so much easier. Okay, so now we can look at an equation and figure out what shape it is. But who cares, right? Why does this actually matter outside of a math class? Well, here's the mind-blowing part. These exact same equations describe how things move through space. Planets, comets, you name it. You know, for hundreds of years, astronomers were convinced that planets moved in perfect circles. It just seemed right, divine, perfect. But then this guy, Johannes Kepler, comes along and makes a truly revolutionary discovery. He proved that planets actually orbit in ellipses. And the sun? It's not even at the center. It's sitting at one of those two focus points. I mean, that one single idea completely changed how we see our entire solar system. And that brings us to one last really cool thought. What if a comet's path is a hyperbola? What does that actually tell us about its trip through our solar system? Well, it means that comet is moving so fast, it has so much energy, that the sun's gravity just isn't strong enough to capture it in an orbit. So it swings by us once, makes its closest pass, and then just keeps right on going, back out into deep space forever. It's never coming back. The math itself tells us the story of this cosmic visitor on a one-way ticket.